I do my best to find some kind of glow. I'm giving it some heart and soul.
Hey Room 21 Rockstars, welcome to our sound and light review. So a couple of things you're going to probably want beside you before you begin this review would include your science book volume 2. We're going to start probably, I would say around page 640 is where the sound unit begins. And then you're just going to want some spare paper or something to write with. If you're in the classroom, you can go get some lined paper, or you can find something at home that you might want to write with as well. You know, I really feel like you guys have the major concepts of the unit down, and that you can just truly explain them, and you know, that you guys truly understand sound and light. But this is going to be a quick little review that kind of pieces together everything for you. So to begin, as we know, sound and light, they are both examples of energy, okay, in different forms. And so I think the biggest comparison that you guys need to think about right now is, what is the one biggest, most important difference between sound and light? If you can think of it right, think of a little hint, I guess, would be, think about how sound and light travel, and that would probably come along as the biggest contrast or the biggest difference between sound and light. Yes, that would be that one requires matter to travel and the other does not. Okay, so which one is which? Think about that right now. Which form of energy, sound or light, requires matter to travel, and which one does not? Well, light does not require any matter. As we know, it gets the whole way from the sun to 93 million miles to us here on Earth. And sound, without matter, sound cannot travel. So if a spaceship blew up beside me in outer space, I would not hear it, okay? Because there's no matter, no particles to vibrate. Okay, so on your sheet of paper, what I want us to do is, we're going to start with light today, okay? And I want you just to quickly draw a light wave, okay? Mine looks a little something like that. And something, you know, as you guys know, we just want to make sure we get down the basic parts of the wave, and these are the same for the sound wave as well. So go ahead and with your wave, go ahead and draw or label the different parts. And those parts would include the trough, okay, that's where the animals eat. The crest, the wavelength, and you can decide what your wavelength you would like it to look like. You can either go from crest to crest or trough to trough. Okay, and I guess the only other one that I want you guys to hone in on would be the amplitude, and I'm actually going to draw my line down the middle and do this. Go ahead and label the amplitude on your light wave, and then check out mine. Okay, so obviously we have the crest, which is the top of the light wave. We have the trough, which is the bottom of the light wave. That's where the animals eat, in the trough, right? And then a wavelength is either from one crest to the next or from one trough to the next. And then the amplitude, the energy of the wave, is from the midpoint of the wave to the trough, or vice versa, from the midpoint down. From the midpoint to the crest, or from the midpoint down to the trough. So make sure you have those four wave parts down. Those are incredibly important. Now, we know that light is on me right now. That's why you see me. Light travels in straight lines in all directions. It scatters out in all directions, and it fits with our math unit right now, with rays, okay? And everything we're working on there with angles, okay? So light does not, and I'm going to write that right here, okay, does not require matter. Now, like we talked about in class, guys, I think the biggest thing I want you to think about when you're thinking about the differences between sound and light is, whenever we're in the middle of a thunderstorm, do you hear the thunder or do you see the flash of lightning first? What do you see first? Okay, yeah, you see the lightning. Okay, so light travels faster than sound, as we know. Sound takes a little bit longer to get here because it has to travel through that matter and has to compress those particles together in order to get to our ears and vibrate those eardrums as well. Okay, so a few other things that we want to make sure we get down with light. First of all would be talking about the electromagnetic spectrum. As we talked about in class, we can only see a tiny, tiny part of all light known to man. So here I have a Sharpie, and on the edge of this Sharpie, or my bracelet here as well, if you look right here, the tip of this cap is red. Okay, and I either want you to write down, explain to somebody at home, explain to somebody in class right now. You can pause the video. Why does the cap of that pen, of the Sharpie, appear to be red? Think about it, pause the video, and then come on back. Okay, guys, so you probably wanted some type of explanation saying that the light waves come to the cap of the marker, and all of the light waves, all the colors of the visible spectrum are absorbed into the cap except for the color red, which is reflected back to our eyes. Okay, so I see a red cap because all the colors of Roy G. Biv are absorbed except for the color red, which is reflected back. So that is why I see a red cap, or for instance, my blue Room 21 Rockstar bracelet, or my black, what about my black shirt? What do you guys think about that one, though? Yeah, that's when all the colors are absorbed, and we know that white is when all the colors are reflected back. And I think the best example is thinking back to the time whenever we had the smartboard on during the City of Ember Day, and we saw the rainbow appear on the ceiling whenever there was a white screen up on the smartboard. And then the rainbow disappeared whenever there was a black screen. So that really brings down that electromagnetic spectrum for us. Now, what I want you guys to do is draw a little graph like this. So on one end I put low frequency, which means how often does the wave occur, to high frequency. Okay. Now we can talk about this with light and sound, but the biggest thing with sound, we see the different colors of the rainbow because each color of the rainbow is a different frequency. Okay. If it didn't have a different wavelength, okay, if each color of the rainbow did not have a different wavelength, we would only see one color. So I want us to think about what color of Roy G. Biv has the short or the lowest frequency, and what color of the rainbow has the highest frequency. And honestly, if you know those two ends, and you can just fill in the rest. Think about that really quickly. Label your diagram. Pause the video if you have to, and then you can come on back. So, what did you guys put for your lowest frequency? I'm drawing mine right now. It should be just like that. It's literally in the order of Roy G. Biv. Okay, because red has the lowest frequency and violet has the highest frequency. And we talked about how green is that one color that just automatically sticks to our eyes. That's why, they use green screens for weather forecasts and different things like that. Our eye is automatically attracted to green. It has that perfect frequency, more so than any other color in the visible light spectrum. So there we are, lowest frequency, highest frequency. So you could say that the waves look a little something like this. If you draw the wavelengths as well. So obviously the wavelengths down here are much larger than the wavelengths up here, because whenever a wave is more frequent or has a higher frequency, the wavelength, because we know wavelength is obviously much shorter. Okay, you don't have to use the scientific formulas like you'll be using in high school to see that this is a much longer wavelength than violet, for instance. Okay, so make sure you have that down. You may want to rewind the video. Think about that again. This is a very important concept. This is the only part of light that we see, which is pretty miraculous if you guys think about it. Okay, and then finally, two other things that I want to talk about with light. Right now, I just want you to either look in the classroom, I want you to look at your house, wherever you are currently at this minute. Write down these three terms on your paper: opaque, transparent, and translucent. And I just want you to list a ton of items under each, because obviously we're talking about how light passes through different objects. So what objects could you put for each of these categories? I'm going to do the same. Pause the video if you need to, and then come on back and share your list with me. Okay, guys, so what did you find for something that's opaque? So obviously, we always have opaque down. That's the thing that nothing can pass through. So for instance, my shirt is opaque. Nothing is passing through it. The wall behind me is opaque. There is no light coming through the wall. Okay, in terms of something that's translucent, remember we always talked about lampshades. Some lampshades, I don't want to classify them all as being translucent. They let some light through, but they don't let it all through. And then when we're talking about things that are transparent, if you look at my water bottle here, the part that has no water, you can see right through to my eyeball, just like that. So that is transparent. The part that has water in, I would probably actually say that it's translucent right now. Okay, so all you want to do is practice at home, classifying a bunch of different objects as transparent, translucent, or opaque. And that'll be a good review for you there. And then when we talk about reflection and refraction, okay, you know, reflection, we know every day we look in the mirror when we wake up, I hope, to make sure we comb our hair before we come to room 21 or brush our teeth or something like that. So reflection is simply when light waves hit a surface and come directly back off. But now that we're talking about angles, it's really cool because if this is my mirror, this line right here, and the light comes in and hits the mirror like that, the light goes out at exactly the same angle. Okay, so the light comes in and then it bounces right back out. Okay, and we're going to be talking about those angles this week in class as being complementary and supplementary. So, see, math isn't science, just like that. Now, refraction is simply whenever some light is absorbed by an object and it ends up bending. So, you know, we talked about the swimming pool, different things like that. I brought along an example of refraction right here. If you look at this glass with my college pencil in, IUP, see that? Look at, and this is a perfect picture on the video screen, actually, guys. Look at the pencil. It appears to be absolutely broken. And it appears to be broken because light bends whenever it hits different forms of matter. Okay, and therefore it bent, and it appears, number one, magnified because light or water is acting as a magnifying glass for us. But it also appears bent, which is an example of refraction, which is the bending of light. So reflection is the bouncing off of light, and refraction is the bending of light. So think about a couple of other examples. You know, we had the rising penny demonstration in class. We had the arrows that switch direction behind cups in class. I had you guys create the laser mazes. We had tons of different examples that you can think about that fit that bill as well. Okay, so I think, and I have the test right here, guys. So like this is like prime opportunity to get some information from Mr. Reichard for the test. I think that I've hit everything that I want to for light. You know, look through your notes just one last time. Just, you know, like we talked about in class, guys, this is not going to be what is this. I want to get into the why and the how of the science that we've been talking about. So really make sure you're able to articulate why different things are certain colors and why we see different colors to begin with. Why do we see red, orange, yellow, green, blue, violet? Why do we not just see one color? And then think back to the City of Ember Day when the lights were absolutely off, okay? And the only thing that you guys saw when I was holding up that construction paper, you saw nothing. I won that game, right? You guys could not guess the color of those colors of paper because the only reason we see color is because of light, okay? Light is color, okay? So think about that, and I think that about does it for the light portion of the review today. Now, sound, if you go ahead and do the same thing with sound, so we said light does not require matter. Here is an example of a light waves. I guess the only other thing you might want to make sure you have down for your light wave, guys, is that it is a transverse wave. You know, I showed you the example of a jump rope as an example of a light wave. Travels in straight lines, spreads out in all directions, and I always think of the sun because that is exactly what it does. Okay. Now, in terms of sound, we know that sound requires matter. Okay. There is no sound without matter. Okay. Or without, yeah, there is no sound without matter. But I want you guys to think about how sound travels. So I would go back to the tuning fork at lab experiment day. Whenever you guys hit the tuning forks softly on your palm, hopefully not too hard, and then you put them into water, the water absolutely just spilled up, right? And that's because the sound waves were vibrating and it pushed the water out of the way. So it proved that sound vibrates matter in order to be transmitted or transmit to us and to our ears. And it vibrates our ears and our eardrums, and then our brain picks up those sound vibrations, and that's why we hear sound. So I drew a sound wave here. Now, take note of how different these look. We use a slinky to represent the sound wave because it's a compression wave, right? It travels in compressions. It's energy passing through matter. the matter is not moving, the energy is moving, right? It's just like the waves in the ocean. The energy is going through the water, which it. Okay, guys, now that you actually have your sound wave drawn, I want you to label the two components of that sound wave, which would be the compression and the rarefaction. You can go ahead and pause the video and then come on back whenever you have those two parts labeled. Okay, guys, so here's what mine looks like. I have my compression. That's where the particles are pressed together, right? That's where the sound vibrations are. And then we also have our rarefaction. And, you know, I would just go back and think about the Slinky example and how those sound waves move from a source to you know, an ear or something that is able to hear them through vibrations, right? And I also drew the particles down here to kind of show you that similar comparison. These would be the compressions, and this would be the rarefaction, okay? So the only other thing that I think we really want to focus in on with sound would be, you know, all of those big terms that you use with your classroom instrument project. So we're talking high and low pitch, we're talking high and low volume, we're talking high and low frequency, and we're talking high and low amplitude, okay? So what I'm going to do is I'm going to play a sound, and then I just want you guys to determine, and you kind of do what we do in class. Go ahead and show me what that wave would look like based on the pitch and the amplitude and the frequency and different things like that. Okay? So the first sound is going to be right in 1 second. Sorry, guys. Okay, here's the first sound. So what would that wave look like? Probably like this, right? It's more of a low pitch. It probably has a high amplitude, a high energy. It's a low pitch, a low volume, a low frequency, all of those different things, right? Let me get to another one. Oop, that's not the sound I was looking for, guys. I'm sorry about that. There we go. Okay, so show me what the wave would look like for that sound. Yeah, it would definitely be much more frequent, okay? And then at the same time, it would also be a high volume, okay? So we have that high frequency, we have the high volume, not as high amplitude, okay? It doesn't have as much energy in it. It's just a high pitch and a high frequency. So I want you guys to think about the relationships between pitch and between frequency and between amplitude and between volume, and just, you know, use some examples. If you're watching TV or playing a video game or anything like that, think about those sounds and think about the different energies that those specific sound waves have and the vibrations, the volume, the pitch, the frequency, the amplitude, etc. Okay, and that would be a good example for you. Also think about the root beer bottles that we have in class, and when we fill them with different amounts of water, the type of pitch that would also create, okay? Now, our final exploration with sound, guys, okay, we know that it requires matter to travel through, and we know that sound travels differently through different forms of matter. You know, I took you outside, and I hit the side of the building with that brick, and each of you put your ear next to it where you could no longer even see me, and that sound was absolutely just amplified. You know, it was so much louder whenever you had your ear against the building, because we know that sound travels fastest through solids, medium through liquids, and slowest through gases. And if you guys actually draw 3 boxes to represent the particles in a solid, a liquid, and a gas, and if we have the particles in a solid, they would look a little something like this. Okay, so there's my solid, okay? And then if I drew my liquid, it might look a little something like this. Okay, liquid right here, right? It takes the shape of its container, but it doesn't have a definite shape because it takes the shape of the container that it's in. And then finally, we have our gas, which would look a little something like this. So sound is definitely the go-to source of matter for, or I'm sorry, a solid is definitely the go-to source of matter for sound to travel through, as we talked about. And as you get to the gas, it gets harder for sound to travel through. You know, yes, I'm speaking through a gas right now, and my my vocal cords are vibrating matter to you through the computer, etc. But sound travels fastest through a solid. And just always think about the brick and the side of the building when we're talking about that. And I think that will be a great example for you to use and to think of whenever we're thinking about how sound travels through different forms of matter. Now, I'm looking really quickly right now at the test, and I think that I have covered all major ideas that you want to, hone in on for the assessment. Guys, you're going to rock on this assessment. I guess the only other area that I would point you toward, if you want a little bit more study time, would be to the very end of your light and sound unit in your book in volume 2. The review begins on 693. It's actually a practice test, but the questions on that practice test on 694, 695 to 696 are actually really good practice questions. I will have the answers posted up on the board beside the smart board on Wednesday morning for you guys to peruse, and you're also going to have some time on Tuesday with the substitute to also review those materials. If you bring in all of your work pages that we worked on today, okay, all of your beautiful study tools, you guys are going to get yourself 20 house points for your house for sticking it through the vodcast and putting forth an amazing amount of effective effort. I'm really proud of you. This unit was so incredibly fun because of your enthusiasm and passion and excitement for learning and wondering about the world around you. So I cannot wait to see you put that same amount of effective effort toward your assessment. So remember, study, study, study. If you have any questions, please do not hesitate to let me know, and I will see you guys later.
I do my best to find some kind of